Section 8 of the Chemistry of Cookery. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Chemistry of Cookery by W. Mattieu Williams. Chapter 8. Stewing. Some of my readers may think that I ought to have treated this in connection with the boiling of meat, as boiling and stewing are commonly regarded as mere modifications of the same process. According to my mode of regarding the subject, i.e., with reference to the object to be obtained, they are opposite processes. The object in the so-called boiling of, say, a leg of mutton, is to raise the temperature of the meat throughout just up to the cooking temperature in such a manner that it shall, as nearly as possible, retain all its juices. The hot water merely operates as a vehicle or medium for conveying the heat. In stewing, nearly all this is reversed. The juices are to be extracted more or less completely, and the water is required to act as a solvent as well as a heat conveyor. Instead of the meat itself surrounding and enveloping the juices as it should when boiled, roasted, grilled, or fried, we demand in a stew that the juices shall surround or envelop the meat. In some cases, the separation of the juices is the sole object, as with the preparation of certain soups and gravies, of which beef tea may be taken as a typical example. Extractum carnis, or Liebig's extract of meat, is beef tea or mutton tea, concentrated by evaporation. The juices of lean meat may be extracted very completely without cooking the meat at all, merely by mincing it and then placing it in cold water. Maceration is the proper name for this treatment. The philosophy of this is interesting and so little understood in the kitchen that I must explain its rudiments. If two liquids capable of mixing together, but of different densities, be placed in the same vessel, the denser at the bottom, they will mix together in defiance of gravitation, the heavy liquid rising and spreading itself throughout the lighter, and the lighter descending and diffusing itself through the heavier. Thus concentrated sulfuric acid, oil of vitriol, which has nearly doubled the density of water, may be placed under water by pouring water in a tall glass jar, and then carefully pouring the acid down a funnel with a long tube, the bottom end of which touches the bottom of the jar. At first the heavy liquid pushes up the lighter, and its upper surface may be distinctly seen with that of the lighter resting upon it. This is better shown if the water be colored by a blue tincture of litmus, which is reddened by the acid. The red stratum indicates the boundaries of the two liquids. Gradually the reddening proceeds upwards and downwards. The whole of the water changes from blue to red, and the acid becomes tinged. Graham worked for many years upon the determination of the laws of this diffusion, and the rates at which different liquids diffused into each other. His method was to fill small jars of uniform size and shape, about 4 ounces capacity, with a saline or other dense solution. Place upon the ground mouth of the jar a plate glass cover, then immerse it, when filled, in a cylindrical glass vessel containing about 20 ounces of distilled water. The cover being very carefully removed, diffusion was allowed to proceed for a given time, and then by analysis the amount of transfer into the distilled water was determined. I must resist the temptation to expound the very interesting results of these researches, merely stating that they prove this diffusion to be no mere accidental mixing, but an action that proceeds with a regularity reducible to simple mathematical laws. One curious fact I may mention, viz. That on comparing the solutions of a number of different salts, those which crystallize in the same forms have similar rates of diffusion. The law that bears the most directly upon cookery is that the quantity of any substance diffused from a solution of uniform strength increases as the temperature rises. The application of this will be seen presently. It may be supposed that if the jar used in Graham's diffusion experiments were tied over with a mechanically airtight and watertight membrane, the brine or other saline solution thus confined in the jar could not diffuse itself into the pure water above and around it. People who are satisfied with anything that stands to reason would be quite sure that a bladder which resists the passage of water, even when the water is pressed up to the bursting point, cannot be permeable to a most gentle and spontaneous flow of the same water. The true philosopher, however, never trusts to any reasoning. not even mathematical demonstration, till its conclusions are verified by observations and experiment. In this case, all rational preconceptions or mathematical calculations based upon the amount of attractive force exerted between the particles of the different liquids are outraged by the facts. If a stout, well-tied bladder that would burst rather than allow a drop of water to be squeezed mechanically through it be partially filled with a solution of common washing soda and then immersed in distilled water, the soda will make its way out of the bladder by passing through its walls, and the pure water will go in at the same time. For if, after some time is allowed, the outer water be tested by dipping it in a strip of red litmus paper, it will be turned blue, showing the presence of the alkali therein, and if the contents of the bladder be weighed or measured, they will be found to have increased by the inflow of fresh water. This inflow is called endosmosis, and the outflow of the solution is called exosmosis. If an India rubber bottle be filled with water and immersed in alcohol or ether, the endosmosis of the spirit will be so powerfully exerted as to distend the bottle considerably. If the bottle be filled with alcohol or ether and surrounded by water, it will nearly empty itself. The force exerted by this action is displayed by the rising of the sap from the rootlets of a forest giant to the cells of its topmost leaves. Not only plants but animals also are complex osmotic machines. There is scarcely any vital function, if any at all, in which this osmosis does not play an important part. I have no doubt that the mental effort I am at this moment exerting is largely dependent upon the endosmosis and exosmosis that is proceeding through the delicate membranes of some of the many miles of blood vessels that ramify through the gray matter of my brain. But I must wander no farther beyond the kitchen, having already said enough to indicate that diosmosis, which is the general term used for expressing the actions of endosmosis and exosmosis as they occur simultaneously, does the work of extracting the permanent juices of meat when it is immersed in either hot or cold water. I say permanent juices with intent, in order to exclude the albumen, which, being coagulable at the lowest cooking temperature, is not permanent. It is one of that class of bodies to which Graham gave the name of colloids, glue-like, such as starch, dextrin, gum, etc., to distinguish them from another class, the crystalloids, or bodies that crystallize on solidification. The latter diffuse and pass through membranes by diosmosis readily, the colloids very sluggishly. Thus a solution of Epsom salts diffuses 7 times as rapidly as albumen and 14 times as rapidly as caramel. The difference is strikingly illustrated by the different diffusibility of a solution of ordinary crystalline sugar and that of barley sugar and caramel, the latter being amorphous or formless colloids that dry into a gummy mass when their solutions are evaporated, instead of forming crystals as the original sugar did. Some of the juices of meat, as already explained, exist between its fibers. Others are within those fibers or cells, enveloped in the sheath or cell membrane. It is evident that the loose or free juices will be extracted by simple diffusion, those enveloped in membranes by exosmosis through the membrane. The result must be the same in both cases. The meat will be permeated by the water, and the surrounding water will be permeated by the juices that originally existed within the meat. As the rate of diffusion, other conditions being equal, is proportionate to the extent of the surface of the diverse liquids that are exposed to each other, and as the rate of diosmosis is similarly proportioned to the exposure of membrane, it is evident that the cutting up of the meat will assist the extraction of its juices by the creation of fresh surfaces. Hence the well-known advantage of mincing in the making of beef tea. It is interesting to observe the condition of lean meat that has thus been minced and exposed for a few hours to these actions by immersion in cold water. On removing and straining such minced meat, it will be found to have lost its color, and if it is now cooked, it is insipid, and even nauseous if eaten in any quantity. It has been given to dogs and cats and pigs. These, after eating a little, refuse to take more, and when supplied with this juiceless meat alone, they languish, become emaciated, and die of starvation if the experiment is continued. Experiments of this kind contributed to the fallacious conclusions of the French academicians. Although the meat from which the juices are thus completely extracted is quite worthless alone, and meat from which they are partially extracted is nearly worthless alone, either of them becomes valuable when eaten with the juices. The stewed beef of the Frenchman would deserve the contempt bestowed upon it by the prejudiced Englishman if it were eaten as the Englishman eats his roast beef. But when preceded by a potage containing the juices of the beef, it is quite as nutritious as if roasted, and more easily digested. Graham found that increase of temperature increases the rate of diffusion of liquids, and in accordance with this, the extraction of the juices of meat is effected more rapidly by warm than by cold water. But there is a limit to this advantage, as will be easily understood from what has already been explained in Chapter 3 concerning the coagulation of albumen, which at the temperature of 134 degrees Fahrenheit begins to show signs of losing its fluidity. At 160 degrees becomes a semi-opaque jelly. At the boiling point of water is a rather tough solid, and if kept at this temperature shrinks and becomes harder and harder, tougher and tougher, till it attains a consistence comparable to that of horn tempered with gutta percha. I have spoken of beef tea or extractum carnis, Liebig's extract of meat, as an extreme case of extracting the juices of meat, and must now explain the difference between this and the juices of an ordinary stew. Supposing the juices of the meat to be extracted by maceration in cold water, and the broth thus obtained to be heated in order to alter its raw flavor, a scum will be seen to rise upon the surface. This is carefully removed in the manufacture of Liebig's extract or in the preparation of beef tea for an invalid. But in thus skimming we remove a highly nutritious constituent, viz. the albumen, which has coagulated during the heating. The pure beef tea, or extractum carnis, contains only the creatinine, the soluble phosphates, the lactic acid, and other non-coagulable saline constituents that are rather stimulating than nutritious, and which, properly speaking, are not digested at all, i.e. they are not converted into chyme in the stomach, do not pass through the pylorus into the duodenum, etc. But instead of this, their dilute solution passes, like the water we drink, directly into the blood by endosmosis through the delicate membrane of that marvelous network of microscopic blood vessels which is spread over the surface of every one of the myriads of little upstanding filaments which, by their aggregation, constitute the villus or velvet coat of the stomach. In some states of prostration, where the blood is insufficiently supplied with these juices, this endosmosis is like pouring new life into the body, but it is not what is required for the normal sustenance of the healthy body. For ordinary food, all the nutritious constituents should be retained, either in the meat itself or in its liquid surrounding. Regarding it theoretically, I should demand the retention of the albumen in the meat and insist upon its remaining there in the condition of tender semi-solidity, corresponding to the white of an egg when perfectly cooked, as described in page 22. Also that the gelatin and fibrin be softened by sufficient digestion in hot water, and that the saline juices, those constituting beef tea, be partially extracted. I say partially because their complete extraction, in the case of the macerated minced meat, would too completely rob the meat of its sapidity. How then may these theoretical desiderata be attained? It is evident from the principles already expounded that cold extraction takes out the albumen, therefore this must be avoided. Also that boiling water will harden the albumen to leathery consistence. This may be shown experimentally by subjecting an ordinary beefsteak to the action of boiling water for about half an hour. It will come out in the abominable condition too often obtained by English cooks when they make an attempt at stewing, an unknown art to the majority of them. Such an ill-used morsel defies the efforts of ordinary human jaws, and is curiously curled and distorted. This toughening and curling is a result of the coagulation, hardening, and shrinkage of the albumen as already described. It is evident, therefore, that neither cold water nor boiling water should be used in stewing, but water at the temperature at which albumen just begins to coagulate, i.e. about 134 degrees, or between this and 160 degrees at the extreme. My definition of stewing demands a qualification as regards the albumen. Although this is one of the juices of the meat when cold, it should not be extracted in ordinary stewing, as it is in the maceration for beef tea, and thereby appear as a scum to be rejected. It should be barely coagulated, and thus retained in the meat in as tender a condition as possible. Being a colloid, see ante, page 115, its liability to fusion is small, but here we encounter a serious difficulty. How is the unscientific cook to determine and maintain this temperature? If you tell her that the water must not boil, she shifts her stewpan to the side of the fire, where it shall only simmer, and she firmly believes that such simmering water has a lower temperature than water that is boiling violently over the fire. It stands to reason that it must be so, and if the experimental philosopher appeals to fact and the evidence of the thermometer, he is a theorist. The French cook escapes this simmering delusion by her common use of the bain-marie, or water bath, as we call it in the laboratory, where it is also largely used for digesting at temperatures below 212 degrees. This is simply a vessel immersed in an outer vessel of water. The water in the outer vessel may boil, but that in the inner vessel cannot, as its evaporation keeps it below the temperature of the water from which its heat is derived. A carpenter's glue pot is a very good and compact form of water bath. Some ironmongers keep in stock a form of water bath which they call a milk scalder. This resembles the glue pot, but has an inner vessel of earthenware, which is, of course, a great improvement upon the carpenter's device, as it may be so easily cleaned. Captain Warren's and other similar cooking pots may be used as water baths by removing the cover of the inner vessel. One of the incidental advantages of the bain-marie is that the stewing may be performed in earthenware or even glass vessels, seeing that they are not directly exposed to the fire. Other forms of such double vessels are obtainable at the best ironmongers. I've lately seen a very neat apparatus of this kind called Dolby's extractor, made by Messrs. Griffiths and Browett of Birmingham. This consists of an earthenware vessel that rests on a ledge and thus hangs in an outer tin plate vessel, but instead of water there is an open air space surrounding the earthenware pot. A top screws over this, and the whole stands in an ordinary saucepan of water. The heat is thus very slowly and steadily communicated through an air bath, and makes excellent beef tea. At temperatures below the boiling point, evaporation proceeds superficially, and the rate of evaporation at a given temperature is proportionate to the surface exposed, irrespective of the total quantity of water. Therefore, the shallower the inner vessel of the bain-marie, and the greater its upper outspread, the lower will be the temperature of its liquid contents when its sides and bottom are heated by boiling water. The water in a basin-shaped inner vessel will have a lower temperature than that in a vessel of similar depth with upright sides, and exposing an equal water surface. A good water bath for stewing may be extemporized by using a common pudding basin, I mean one with projecting rim, as used for tying down the pudding cloth, and selecting a saucepan just big enough for this to drop into, and rest upon its rim. Put the meat, etc., to be stewed into the basin, pour hot water over them, and hot water into the basin, so that the basin shall be in a water bath. Then let this outer water simmer very gently so as not to jump the basin with its steam. Stew thus for about double the time usually prescribed in English cookery books, and compare the result with similar materials stewed in boiling or simmering water. I have already, page 91, referred to the frying that in most cases should precede stewing. It not only supplies the caramel browning there described, but moderates the extraction of the juices, which, as I have said above, is desirable on the part of the meat itself when gravy is not the primary object. Some further explanation is here necessary, as it is quite possible to obtain what commonly passes for tenderness by a very flagrant violation of the principles above expounded. This is done on a large scale and in extreme degree in the preparation of ordinary Australian tinned meat. A number of tins are filled with the meat and soldered down close, all but a small pinhole. They are then placed in a bath charged with a saline substance such as chloride of zinc, which has a higher boiling point than water. This is heated up to its boiling point, and consequently the water which is in the tins with the meat boils vigorously, and a jet of steam mixed with air blows from the pinhole. When all the air is expelled and the jet is of pure steam only, a difference detected at once by the trained expert, the tin is removed and a little melted solder skillfully dropped on the hole to seal the tin hermetically. An examination of one of these tins will show this final soldering with, in some cases, a flat below to prevent any solder from falling in amongst the meat. The object of this is to exclude all air, for if only a very small quantity remains, oxidation and putrefaction speedily ensues, as shown by a bulging of the tins instead of the partial collapse that should occur when the steam condenses, the display of which collapse is an indication of the good quality of the contents. By good quality I mean good of its kind, but as everybody knows who has tried beef and mutton thus prepared, it is not satisfactory. The preservation from putrefactive decomposition is perfectly successful, and all the original constituents of the meat are there. It is apparently tender, but practically tough, i.e., it falls to pieces at a mere touch of the knife, but these fragments offer to the teeth a peculiar resistance to proper mastication. I may describe their condition as one of pertinacious fibrosity. The fibers separate, but they are stubborn fibers still. This is a very serious matter, for were it otherwise, the great problem of supplying our dense population with an abundance of cheap animal food would have been solved about 20 years ago. As it is, the plain tinned meat enterprise has not developed to any important extent beyond affording a variation with salt junk on board ship. What is the rationale of this defect? Beyond the general statement that the meat is overdone, I have met with no attempt at explanation, but am not therefore disposed to give up the riddle without attempting a solution. Reverting to what I have already said concerning the action of heat on the constituents of flesh, it is evident that in the first place the long exposure to the boiling point must harden the albumen. Syntonin, or muscle fibrin, the material of the ultimate contractile fibers of the muscle, is coagulated by boiling water, and further hardened by continuous boiling, in the same manner as albumen. Thus the muscle fibers themselves and the lubricating liquor in which they are embedded must be simultaneously toughened by the method above described, and this explains the pertinacious fibrosity of the result. But how is the apparent tenderness, the facile separation of the fibers of the same meat produced? A little further examination of the anatomy and chemistry of muscle will, I think, explain this quite satisfactorily. The ultimate fibers of the muscle are enveloped in a very delicate membrane. A bundle of these is again enveloped in a somewhat stronger membrane, areolar tissue, and a number of these bundles of fasciculi are further enveloped in a proportionally stronger sheath of similar membrane. All these binding membranes are mainly composed of gelatin, or the substance which produces gelatin when boiled. The boiling that is necessary to drive out all the air from the tins is sufficient to dissolve this and effect that easy separability of the muscle fibers, or fasciculi of fibers, that gives to such overcooked meat its fictitious tenderness. I am, however, doubtful whether all the gelatin of these membranes is thus dissolved. The jelly existing in the tins show that some is dissolved and hydrated, if my theory of the cookery is right. But there does not appear to be as much of this jelly as would be formed by the stewing of a corresponding quantity of meat at a lower temperature. Some of the membranous gelatin is, I suspect, dehydrated when the highest temperature of the process is attained, i.e., when the concentration of the juices raises the boiling point of their solution considerably above that of pure water. This, if I am right, would check further solution of the membrane, would hydrate and harden the remainder, and thus contribute to the hardening of the fiber above described. I have entered into these anatomical and chemical details because it is only by understanding them that the difference between true tenderness and spurious tenderness of stewed meat can be soundly understood, especially in this country, where stewed meats are despised because scientific stewing is practically and generally an unknown art. Ask an English cook the difference between boiled beef or mutton and stewed beef or mutton, and in 99 cases out of 100 her reply will be to the effect that stewed meat is that which has been boiled or simmered for a longer time than the boiled meat. She proceeds in accordance with this definition when making an Irish stew or similar dish, by simmering at 212 degrees until, by the coagulation and hardening of the albumen and syntonin, a leathery mass is obtained. Then she continues the simmering until the gelatin of the areolar tissue is partially dissolved, and the toughened fibers separate or become readily separable. Having achieved this disintegration, she supposes the meat to be tender, the fact being that the fibers individually are tougher than they were at the leathery stage. The mischief is not limited to the destruction of the flavor of the meat, but includes the destruction of the nutritive value of its solid portion by rendering it all indigestible, with the exception of the gelatin, which is dissolved in the gravy. This exception should be duly noted, inasmuch as it is the one redeeming feature of such proceeding that renders it fairly well adapted for the cookery of such meat as cow heels, sheep's trotters, calves' heads, shins of beef, knuckles of veal, and other viands, which consist mainly of membranous tendinous or integumentary matter composed of gelatin. To treat the prime parts of good beef or mutton in this manner is to perpetuate a domestic atrocity. I may here mention an experiment that I have made lately. I killed a superannuated hen, more than 6 years old, but otherwise in very good condition. Cooked in the ordinary way, she would have been uneatably tough. Instead of being thus cooked, she was gently stewed about 4 hours. I cannot guarantee to the maintenance of the theoretical temperature, having suspicion of some simmering. After this she was left in the water until it cooled, and on the following day was roasted in the usual manner, i.e. in a roasting oven. The result was excellent, as tender as a full-grown chicken roasted in the ordinary way, and of quite equal flavor, in spite of the very good broth obtained by the preliminary stewing. This surprised me. I anticipated the softening of the tendons and ligaments, but supposed that the extraction of the juices would have spoiled the flavor. It must have diluted it, and that so much remained was probably due to the fact that an old fowl is more fully flavored than a young chicken. The usual farmhouse method of cooking old hens is to stew them simply, the rule in the Midlands being 1 hour in the pot for every year of age. The feature of the above experiment was the supplementary roasting. As the laying season comes to an end, old hens become a drug in the market, and those among my readers who have not a hen roost of their own will much oblige their poulterers by ordering a hen that is warranted to be 4 years old or upwards. If he deals fairly, he will supply a specimen upon which they may repeat my experiment very cheaply. It offers the double economy of utilizing a nearly waste product and obtaining chicken broth and roast fowl simultaneously. Another experiment on the cooking of old hens was recently made by a neighbor at my suggestion, and proved very successful. The bird was cut up and gently stewed in fat, like the small joints of my experiments described in page 57. I have not yet repeated this experiment, but when I do, shall use bacon liquor, the surplus fat from grilled bacon, for the bath, and hope thereby to obtain an approach to the effect of larding as practiced in luxurious cookery. One of the great advantages of stewing is that it affords a means of obtaining a savory and very wholesome dish at a minimum of cost. A small piece of meat may be stewed with a large quantity of vegetables, the juice of the meat savoring the whole. Besides this, it costs far less fuel than roasting. The wife of the French or Swiss landed proprietor, i.e. a working peasant, cooks the family dinner with less than a tenth of the expenditure of fuel used in England for the preparation of an inferior meal. A little charcoal under her bain-marie does it all. The economy of time corresponds to the economy of fuel. for the mixture of viands required for the stew, once put into the pot, is left to itself until dinner time, or at most an occasional stirring of fresh charcoal into the embers is all that is demanded. Section 8.